It's my Horowitz. Dr. Horowitz completed his master's and PhD degrees in exercise physiology at the University of Texas at Austin in 1992 and 1996, respectively. He did his postdoctoral training at the Washington University School of Medicine from 1996 through 1999. Dr. Horowitz started as an assistant professor at the School of Kinesiology at the University of Michigan in Ann Arbor in 2000 and rose through the ranks to become a full professor in 2012. He's currently a professor of movement science and director of the Substrate Metabolism Lab at the University of Michigan School of Kinesiology. Dr. Horowitz's lab studies the regulation of fuel mobilization and oxidation and the impact of this regulation on human health. He has received more than 4.5 million grant funding from organizations such as the American Diabetes Association, the National Institute of Health. He's well published and has about 70 peer-reviewed publications to his credit. Dr. Horowitz has about 7 invited reviews and book chapters. He has given multiple invited lectures and keynote addresses at several professional meetings. He's a fellow of the American College of Sports Medicine and National Academy of Kinesiology. He's also a member of the American Physiological Society, American Diabetes Association, and American Society for Nutrition. Dr. Horowitz has a lot of prestigious honors under his belt, some of which include being inducted into the National Academy of Kinesiology in 2020, and also winning the University of Michigan Kinesiology Research Excellence Award in 2018. For service, Dr. Horowitz served on the clinical and integrative diabetes and obesity of the NIH from 2011. Brought back to serving on that study section since 2018. Is an ad hoc reviewer for multiple journals for nutrition and physiology, such as AJCN, British Journal of Nutrition, Cell Metabolism, American Journal of Physiology, just to mention a few. It's my unique honor again to welcome him. And today he's going to talk to us about the effect of exercise on fatty acid metabolism. So welcome.
Well, thank you. That makes me feel like I'm busy. That's great. Thanks for that introduction, and thank you for the invitation to come here. And it was delayed a bit, but I'm so happy to be here. And I've really enjoyed my whirlwind tour and meeting, many faculty. Some I know from before, and some that I'm meeting for the first time. And the students, had a wonderful lunch with the students, and you have a really great group here. And it's really quite impressive. The collegiality and that is the most important, I think, from a graduate student perspective and a junior faculty perspective, probably a senior faculty perspective. It gives joy to being around when you like the people you're working with. That's the case here. So that's been a fabulous insight to this invitation that I received. That's great. So I also appreciate the opportunity to share with you some of the work that we have done in the past, some of our more recent work, and also I'm taking the liberty to share with you some hypothetical, some thinking that have been doing for a while and trying to get some traction with it. And I'm open to a lively discussion. Some may think that what I'm saying is a little off kilter. So I'm happy to get some great feedback after the talk. So I do a lot of work in metabolism, obesity, obesity-related diseases, in particular diabetes and prediabetes, insulin resistance being the focus. A lot of work, most of the work that I've published so far has been mostly in muscle, and I'll talk some about that. And we're transitioning back. I was just mentioning that my earlier career, my postdoc, I did a lot of, and I've always done a lot of lipolysis, but very interested in adipose tissue regulation. But now we're doing a bit more deeper dive into adipose tissue, and that's part of the angle I think that some of you might feel might be off the rails, and I'd be open to interesting and engaged conversation about that. All right, so I think I need to click on this. So one of the features, one of the main issues that my lab focuses on in terms of the health outcome in obesity and relates to insulin resistance and diabetes is systemic fatty acid mobilization is very high in obesity. And I share with you some data from Jill from back when she was a postdoc at Mayo Clinic. And I share with you this because to my knowledge, this is the first, and I'll explain what you're seeing here, but this is the first that I'm aware of where these data were demonstrated that obese, and especially abdominally obese, a lot of people with upper body, abdominal, subcutaneous, a lot of subcutaneous abdominal adipose tissue have excessive, very high rates of lipolysis and fatty acid delivery into the systemic circulation. So these are data from that I took from her paper and created this figure. And we and many others have shown this to be the case. And in this case, and many cases that we in my lab showed, 30 to 50% greater, sometimes it depends largely on the magnitude of the level of obesity, but it can be as 50, 60, 70% greater rates of fatty acid delivery into the circulation compared with a lean or non-obese population. And this, as I'll share with you, if you're not already familiar, this is, I believe, a really key component to the underlying metabolic dysfunction in obesity. So, and as many of you already are in the world of kinetics and are already familiar with this, I know that may be a mixed audience. So, and I apologize, there may be a lot of stuff, there's going to be a lot of pedestrian kind of explanation. So I do apologize for those who are more advanced. But so I just want to clarify that this is not a concentration measure. Oftentimes in obesity, obese actually have very similar concentrations as lean. And the reason is their rates of delivery into the circulation may be very high, but so is their rate of uptake. And that therein lies the problem. So what we have here, again, and these are stabilized measurements of kinetics and the delivery of fatty acids from adipose tissue into the circulation, matched by high rates of uptake into tissues. And again, fatty acids should go to tissues like muscle and liver, but the excessive abundance is the problem. And again, that's what I'm going to beat you over the head a bit with in the of how important that is. So, and we and others have found, this is a few years ago, that showed this relationship between those who, try to use my cursor here, those who release high rate of fatty acids at high rates. This is a relatively homogeneous population of obese adults. And yet, despite their presentation as being homogeneous in the context of the BMI, adipose tissue mass, location, so all abdominally obese. Despite that, there's a wide range of insulin sensitivity, in this case measured by clamp. And those who release large amounts of fatty acids were much more insulin resistant, lower insulin sensitive, right? Certainly doesn't show cause and effect, but relationships like this hint at the notion that it may be the case. And again, I would argue that it is an important case, and I'll share with you some data about that. So I want to talk a little bit about, and again, I apologize for the simplicity of some of these cartoons, but I want to talk a little bit about how might that happen? How do fatty acids, how does excessive availability of fatty acids interfere with insulin? Again, I'm going to focus on insulin signaling and insulin sensitivity. So I'm not going to get into the details, but this is, as you are more than likely familiar with, insulin's binding the receptor, the cascade of phosphorylation events that lead to the glucose transporter getting to the membrane so glucose can enter the cell, right? So I'm not going to get into details with that. So move that to the side. My goal in this slide right now is to show you how does fatty acid interfere. So first I want to talk about what happens to fatty acid. What are the primary fates of fatty acid? And again, oversimplification. But when fatty acids enter the cell, they have what I view as two primary fates. One is to the mind, and this is a muscle. The red portion down there is depicting a muscle. A muscle cell, and so it can go to the mitochondria to be oxidized for energy. The other primary delivery or deposit site is to be reesterified and form intracellular lipids, or intracellular triglycerides. Two primary fates. And a secondary fate that is an accumulation of what's often referred to as fatty acid metabolites or fatty acid intermediates, such as DAG or diacylglycerides and ceramide and a host of other intermediates. So that is, those again, in simple terms, are the routes at which fatty acids and the primary fates of the fatty acids. When fatty acid availability is high, it can outstrip its ability to be stored effectively or oxidized. And when you get free radical formation, increase in hydrogen peroxide, and those events in themselves can induce meaningful damage and dysfunction among many signaling pathways, including the insulin signaling pathway. And also, because if you are fatty acids uptake and have fatty acid availability out there, but when fatty acid availability is high, in general, uptake is very high. And so when uptake outstrips its ability to be oxidized or stored locally within the muscle cell, then these fatty acid intermediates can increase, diacylglyceride ceramide, which leads to some inflammatory pathway activation that interfere with the insulin signaling pathway, inducing insulin resistance. Okay, so again, we'll come back to this quite a few times, but just want to set the table. And again, I apologize for those. This is a massive oversimplification review. So what I want to talk about in this early portion of the talk is how weight loss and exercise influence this event. This may be called fatty acid induced insulin resistance is how it's often referred to, or I refer to it as. And one thing I want to mention, and I know some of you are very engaged in this separation as well, but I want to clarify, even though clinically weight loss and exercise are, prescribed simultaneously, it's very important. In my team, we spent a lot of time and energy and effort separating the effects of weight loss and the effects of exercise. And the reason, a little bit of a tangent here, I just want to, why bother? If that's how people do it, that's why people, that's what clinicians do, and that's what people are ingrained in them. A person who is maybe overweight or obese, ingrained in them, eat less, exercise more, same time, right? So a couple of arguments against or why to separate. One is, these are two of the most challenging interventions or behavioral changes that you can think of for someone who is not accustomed to that. And they're very different, right? And so again, apologies for the simplification. If I'm not a unicyclist and I don't juggle, but I imagine if I did them, I wanted to become one, I wouldn't try to juggle start juggling and unicycling at the same time. I do one first and then the other, right? And I'm not a behavioralist, a behavioral psychologist. I am married to one, and she feels the same way as I do. And maybe I got that information from her, but it just seems so obvious, and maybe we should think. Anyway, the talk isn't about that, but I think that's an important element. Another argument is exercise programs, as many of you are familiar with, in the long term, in the short term, maybe there's some weight loss induced, but if you just tell a person to exercise, there's often compensational eating, and they don't typically lose weight. Typically can anecdotally, but typically don't lose weight in the long term, right? So in a sense, exercise can occur in a vacuum of sorts, and so it is important to look at it in that case. And more relevant to what I'll be talking about today is the mechanisms underlying these two things are very different, and if you have them both overlapping at the same time, you don't understand what's happening. And again, based on bullets 1 and 2, maybe we really do need to understand what's happening individually. All right, so I want to talk a little bit first about weight loss only, no exercise, right? And weight loss, it's well known, and I'm sure you're all familiar with the notion, and not notion, I would even call it a fact, that weight loss, while it may not disappear insulin, and make insulin resistance disappear, in some cases it can, but it certainly almost always reduces insulin resistance very meaningfully. Even modest, very small amounts of body weight loss and fat loss can induce impressive improvements in insulin sensitivity. You should be familiar with that. I argue, and I'll share with you the data that makes me argue that much of this effect is due to the reduction in fat mass and the reduction, as a consequence of reduction in subcutaneous fat mass, that fatty acid mobilization goes down. And that's a big feature, I would argue a major feature, why weight loss improves insulin sensitivity. And why do I say that? Based on these data, among others. These are data that from my lab a number of years ago. But we had subjects, obese subjects, pre-diabetic, lose 12% of their body weight. And we measured their fatty acid with tracer kinetics, measured fatty acid, and I'll call it mobilization, so fatty acid rate of appearance, rate of disappearance. And as a consequence of their weight loss, and they all lost 12% of their body weight, fatty acid availability and uptake went down, okay? And then, same study, same day, same trial day, we measured their insulin sensitivity, right? We used the IVGTT in this case, right? And it went up, right? And if I stop there, hopefully you would roll your eyes and tell me that that's not saying that this causes this, right? So hopefully that's the case. But, and I would agree with you. But what we did was we had these people after the weight loss, they came back for another visit. So they're the same, they maintained their weight loss. And a few days later, they came back and we infused them with lipid and heparin to increase their fatty acid availability. And not just arbitrarily, we titrated it so it matched their pre-weight loss fatty acid availability. So in theory, they're still this person who's adapted and changed in response to the weight loss intervention. In this case, again, is dietary only. And we matched their fatty acid rate of appearance. Then the question is, well, what happened to insulin sensitivity? Basically completely reversed. These are people who are, 12% lower body fat. They're a few days removed from the red bar there, but the only change was it was an overnight infusion. We probably didn't need to do it even overnight, but an overnight infusion of fatty acids to elevate their fatty acid availability back to what they were before weight loss. So to me, as the green title here says, is the reduction in systemic fatty acid availability is key to the insulin sensitivity, sensitizing effects of weight loss. And I would love to argue that it's really the only thing going on. It's certainly not the only thing going on, but I think it's a very, very important feature. All right. So what about exercise training? Right. So we know adaptations to exercise training do a lot of different great things. And one of them is to increase mitochondrial content and increase the oxidative capacity, which in this model seems like a very favorable event for funneling this excessive fatty acid availability. And so we looked at that question. So with our subjects, so the subjects in this study were randomized to what I showed you before, a diet only or a weight loss and diet. A weight loss and exercise program, same dietary intervention. And our endpoint, importantly, was the 12% body weight. It was not a 6-month or 4-month intervention. It is a confounder that some lost weight a little faster than others. In general, the exercisers did, as you might expect, did lose weight. And so fair, that is a confounder. I believe that it's a much bigger confounder if they would have lost different amounts of body fat, because that's really the question we're trying to tackle. So just to show you that the exercisers improved their VO2 peak, and this is liters per minute, so they lost body weight. So if I did it per kilogram body weight, it would look even bigger. But this is absolutely, we took biopsies, we measured mitochondrial markers, they were up. So things, as you might expect, and just proof of principle that they were adapting to the training. It was 4 days a week, moderate, vigorous intensity. And so here's the insulin sensitivity data that I showed you before. This is the weight loss group. Again, same study, subjects randomized to either this group or the exercise group, the weight loss plus exercise. We found no difference, right? And as an exercise physiologist and exercise enthusiast, maybe a kick to the belly well, why did they bother with the exercise? Importantly, and I'll get to in a few minutes, that we, again, matched for weight loss, that's important. And also we made these measurements 3 days after their last exercise training session. So we removed, as many of you are familiar with, the importance of the most acute session. If you're not familiar with it, you will be in a moment, because I'll share with you some data along those lines. So we removed that. So this is really looking at the adaptations to training. They're no more untrained, but we're removing the events and the energy expenditure and the change in glycogen, whatever that might be, and substrate flux is associated with the acute session of exercise, right? And it really, to be honest, it wasn't a surprise to us, because there are many studies that when you control for body weight, either have them make weight maintain or lose the same amount of weight and remove the session of exercise, that there's often found no difference in insulin sensitivity if you control for those factors. So this is some data from Bob Ross showing that they looked at 12 weeks of exercise training in lean, obese, and diabetic. So the yellow is the pre-training, 12 weeks later, the post. They did the same thing in terms of in this case, it was no weight loss, and they removed the last exercise session. And the blue bars are the same height as the others. In both cases, you can see the graded reduction in insulin sensitivity, as you might expect with lean to obese to diabetic. But the blue to yellow is the comparison that I want to point out. And there are many studies, and I would argue most studies would, if when controlled well, demonstrate that the training adaptations are minimal, if at all, exist in terms of insulin sensitized. So what about fatty acid? So what about, that was under this weight loss the data I shared with you before in terms of our scenario. But we have that fatty acid-induced insulin resistance, having more mitochondria when we bombard them. So we did this lipid infusion again. When we bombard them with lipid, now they have a better place to put it, and we're going to see some improvements. And so here again here are the data that I showed you before with the weight loss only. Here are the weight loss improvement, and with the lipid infusion, same thing. Having more mitochondria, and I'll use that as the sole adaptation, but a lot of things are obviously going on with exercise, but adaptations to training, like increasing mitochondria, did not improve insulin sensitivity per se when we removed the last session of exercise. And it sort of makes sense because at rest, when these measurements are taken and when most people live their normal lives, resting, having more mitochondria is great for when it allows you to exercise harder, longer. But at rest, there's already enough in people who don't have mitochondrial challenges. In general, there's largely, and I guess I would argue, enough mitochondria to deal with the energy expenditure that's happening at rest. Exercise is a different matter, and that's what the adaptations to training are really happening, is to enhance your ability. The signals are in place to increase your capacity to exercise harder or longer. Okay, so exercise training, big question mark, and again, adaptations to training. But is that all that's happening with exercise? And no, it's not. I want to share with you that again, it is controversial. If I polled people before they came in the room and I said, hey, does exercise training improve insulin sensitivity? My guess is most people would say yes. Many of my colleagues would say yes. And there are studies that report, and this is one of them, that the answer is yes. So this is from the STRIDE study, so a very large randomized control trial. They found 10 to 15% improvement. This is after training. They did lose, in my cynical view, they lost a significant, but 1 to 2 kilos, so not a lot, but a little can go a long way. But they showed increase 10% or so increase in insulin sensitivity. So there are data out there certainly that support the notion that training improves insulin sensitivity. But when they do, it's pretty modest. Right. The other reason I'm showing you this, actually the main reason, is what they did in the study. Not only did they look at it after controlling for the last session of exercise, they looked at it the day after the last session of exercise. And as many of you are aware, and as I foreshadowed before, exercise has a potent acute effect of improvement in insulin sensitivity, and that's powerful. Right. And hard to argue that the magnitude, and this is consistent with many other studies, hard to argue that the magnitude of increase, if you're talking about what is the benefit of exercise, it's what you've done for me lately, rather than the adaptive responses. Even if you see a significance in the adaptive responses, the what have you done for me lately is the more potent and important element. And so rather than 10 to 15%, we're talking 30 to 50% improvement in insulin sensitivity. It wears off. Next day, maybe goes into the next day, depends on the eating behavior, a lot of things that I don't have time to chat about. But the acute effect is really powerful. So we wanted to explore this, does exercise do something to an obese person? Or actually in this model, I used lean people and infused them with lipid to model an obese phenotype in terms of their fatty acid availability. But the question was, does an acute session of exercise protect against this excessive fatty acid availability? And what we found, so we take, again, lean, in this case it was all women, lean women, infused them with, had them exercise once in the evening or afternoon on one day, infuse them with lipid overnight, and measure them measurements the next morning, versus same people coming back, or again, randomized order, but they didn't exercise. They had the same lipid infusion. Right? So I'll just talk through the results through this cartoon for the sake of time. So this is, and this isn't trivial. This is the acute effect of exercise. Like, I used to tell my colleagues, like, acute effects of exercise. So I only have to exercise once. That's great. So it's really what's happening with each time you exercise. It's your dose. What happens? And so what we found, again, I'll just step through this with a cartoon. So as you might expect, energy expenditure and fat oxidation was elevated for several hours after the exercise session. So some of the fatty acids were funneling toward the mitochondria to a greater extent. We also found, more interestingly and more novel, was that actually the exercise session induced an increase in intramyocellular triglycerides, and we found proteins involved in that pathway. The proteins themselves, we measured the activity of the proteins, but the proteins themselves the next day in muscle biopsy samples were up. And and I won't get into the athlete's paradox, but this could help explain athlete's paradox for those. Again, I'm not going to go into details about that for sake of time, already taking too much time. But for those who are familiar with the athlete's paradox, this might help explain that phenomenon. As a consequence of what I will call more favorable a disposal of the excessive fatty acids that we were providing to the mitochondria for oxidation or storage in neutral lipid within the muscle, we found that the accumulation of diacylglyceride and ceramide were reduced. So the yellow bar was significantly lower. In the exercise condition, again, they got the same lipid overnight. Inflammatory markers, in this case, this phosphorylated junk as an indicator of inflammatory markers, were down. And insulin resistance was completely, it actually was even greater than their baseline insulin sensitivity, despite being infused with lipid overnight. So the acute effect of exercise has a very potent effect on insulin sensitivity that we know. And we believe much of this in an obese model, again, we're modeling obesity, is this repartitioning of the fatty acids as a consequence of what you've done for me lately. Of today's exercise helps refunnel my elevated fatty acid flux, helps it partition to more favorable disposal routes and reduce the inflammatory insult and the more dysfunctional pathways involved. All right, so that's great, and that may be an important element, the important element of one of the more important elements of exercise training is each day of exercise, but it still feels like a Band-Aid. And the real problem is really this excessive fatty acid, right? And so, as I showed you before, weight loss will reduce it, but weight loss success is not so great. But we wanted to understand more about this. What can we do to help circumvent? There are drugs that can reduce fatty acid, beta lipolysis, and those do indeed are insulin sensitizing. But we want to look at exercise physiology. I want to look at the role of exercise, and I want to go to the source. So I want to look at subcutaneous adipose tissue and how exercise plays a role in modifying, perhaps, this is where we're getting to the more hypothetical elements. Talk here. So how exercise may modify subcutaneous adipose tissue in ways to be more favorable in terms of fatty acid, the overall fatty acid exposure. So I know that some of you are already in this realm of exercise and adipose tissue, but compared with other tissues, especially skeletal muscle, it's a really understudied area, right? It's not scratching the surface, right? Comparatively, but again, some of you are already in this space and doing great stuff. Some of the work that's been done certainly is looking at role of exercise in beiging or browning of adipose tissue. Really cool work being done in that arena. Work done on how exercise may impact adipokine release, peptides. And we know that adipose tissues is a really important endocrine function and releases a bunch of peptides, bioactive peptides that are important. Also, I don't have on the screen, but how exercise may impact inflammatory insult and macrophage infiltration into the adipose tissue. And those are great. That's not where we're particularly focused on. We're focused on something else. We're focused on the role of exercise on adipose tissue expandability. Right? And again, I apologize and appreciate that some of you are already certainly aware of this concept of adipose, or the expandability hypothesis that I will talk about in a second. But just to share, and I'll overdo it, but I'll share with you a couple of things. We think that exercise, and again, evidence-based, that exercise may increase the ability of adipose tissue to expand. Its capacity to expand is enhanced as a consequence of the hypothesis in response to exercise. Okay, so for those that are not familiar with expandability and this notion that seems really crazy, I want to kind of maybe help reframe what adipose tissue is. And many of you may think of adipose tissue as something like this, and it's the tissue you love to hate, and it's really, maybe it's healthful, but I really hate it, and it's really not. And instead of thinking about images like this and giving it the bad rap, I want you to think of, instead of this, I want you to think of this, a suitcase. Bear with me. When we travel, let me back. When I travel, I overpack, always. I'm here for 2 days. I pack 3 times as much as I need, right? My family is worse. Well, my son is great. My wife is worse. And so what do you do? if you overpack, or you've gone on your trip and brought a bunch of souvenirs or extra trinkets, or what do you buy? An extra bag and then pay extra fees to bring your stuff home. Or you could think ahead, like, hey, I might be, and get an expandable suitcase, right? And importantly, the expandable suitcase is not making me overpack, right? Much like adipose tissue that can expand healthfully, has the capacity to expand, is not making me fatter. Okay. And much like an expandable suitcase, and if you don't overpack, just never unzip the expandable part. Right? No harm, no foul, nothing. It's all good. So, and like an expandable suitcase, where things have to, the zippers have to work, the flexi material can't be brittle, right? The zippers have to work well in order for it to function well. Okay, so hopefully that analogy kind of worked. All right. So I want to explain this a little more mechanistically, and more physiologically in terms of this expandability hypothesis. I'm looking for time. All right, someone might need to yank me if I go long, so I apologize. Or give me a 5-minute warning or something. So again, adipose tissue is known to be an important source of a lot of bioactive important peptides, right? And no question, really important stuff. But it also, we can't lose sight of the fact that its main role is to store energy in the form of triglycerides and deliver that energy in the form of fatty acids to different tissues, right? And so that's really where I'm going to focus the energy here, right? So maybe pancreas, muscle, liver, and again, should go. Needs fat. Those tissues need the energy from fat, especially when between meals or you haven't eaten for a while. So those are important things, right? But when those rates, as I mentioned before, obese adults, obese people have elevated rates of fatty acid mobilization. And when those rates are very high and going excessively to these tissues and others, at the muscle level becomes insulin resistant, as I mentioned before. It in the pancreas reduces insulin secretion. In the liver, a whole host, and I know many of you are embedded in the hepatic world and the liver world, and understand and value the importance of these maladies, right? And excessive fatty acid mobilization and delivery and uptake to the tissue clearly is a problem, right? So what about this expandability hypothesis? So again, I apologize for beating this over the head, but I want to show you this mechanistically and kind of tell you about our working hypothesis. So when we overeat, and I'm not just talking about a big meal, I'm talking overeating to the point where we're really gaining meaningful amounts of weight. If we can expand the adipose tissue, the storage capacity effectively, which I'll get to in a moment, then fatty acid flux to the tissues can maintain, that energy is being stored where it's supposed to be stored. Air quotes on that, right? But unfortunately, there is a limit to the capacity, and we have a limited capacity. Some, again, all have a cap to that capacity, but some have more of a restricted capacity to expand. And we're really interested in and if that's the case, then you overeat and gain weight, then that fat has to go somewhere, and it's going to the other tissues, right? So we're really interested in what's that lock, what's keeping an adipose tissue, what's preventing an adipose tissue from expanding more effectively. And can we do anything, and importantly in our case, can exercise do anything to tweak that effect to enhance our capacity to store fat? And again, you tell your friends about, oh yeah, storing fat is good, they'll think you're crazy, as many think I am. But I hope that what I've explained so far makes sense. And again, I appreciate that many have been on that page from my first slide on that. So I want to talk a little bit about adipose tissue and what this, what maladaptive response, and again, overly simplified, but when a lean person gains weight, classified 2 different bins of developmental weight. The more unfavorable on the left side of this slide, where you have a limited, so these red lines of the capillary, so really no additional capillary growth. These hatches are indicative of fibrosis, so more fibrotic, the larger hypertrophied cells that aren't being fed really well by the capillary and blood flow to the tissue, resulting in more macrophage infiltration into the tissue and higher release of fatty acids, versus the more metabolically favorable increased capillary growth, smaller cells, maybe formation of new cells, so keeping them smaller. So even if there's more capillaries, plus the fact that there's a smaller cell, to the delivery to the cell itself would be enhanced, less hypoxia, less fibrosis noted by the hatches, less macrophage infiltration. So the more metabolically favorable versus metabolically unfavorable. And now finally getting to our working hypothesis about exercise is that regular exercise, again, hypothetically, we believe primes subcutaneous. So regular exercise primes subcutaneous adipose tissue for more effective energy storage during those episodes of energy surplus and weight gain, right? So cartoon-wise, the sedentary person who gains weight and is a non-exerciser and continues to gain weight and non-exercise, they may follow the more metabolically unfavorable path versus someone who may be a regular exerciser, but regular exercisers gain weight, and that may lead to a more metabolically favorable. And again, in the model here, for the same degree of fat gain, and so the same degree of overeating, right? So you might stop there and say, exercise and weight gain, that is so out there, because that's not what we do. And it might, the images I showed you there, I might get images like this, crazy images of Ronald McDonald overeating on a treadmill. But rather than think of silly images like this, I want you to think of data like these, which is BMI gain or weight gain as we get older, right? And what happens? Population, and again, this is one of many studies, and I'm sure this is not any new information to anybody, that through middle ages at least, most people gain weight and gain fat. So the question really boils down from a practical perspective is, does regular exercise behavior modify adipose tissue in ways that makes it better to accommodate this extra weight gain that most of us will experience as we age and over time? Right? We can't do the study over 40 years, but we can try to hint at what might be happening. So the last portion of the talk, I want to talk about what we think might be happening, how exercise may be doing this more favorable adaptive responses. And I'll talk about 4 different quadrants or 4 different areas that we think that exercise may be playing a role. So one is adipogenesis, so new cell formation. Does exercise, again, may seem really counterintuitive, but does exercise induce an increase in new cell formation? Right? So pause there. Does it modify the fibrotic component, the extracellular matrix that's holding the tissue together? Does it remodel the extracellular matrix? Does it induce changes in angiogenesis to increase blood flow delivery to the growing fat tissue? And does it modify adipose tissue inflammation, right? So I'm going to talk a little bit about each of these in the remainder of my talk. So first, adipogenesis. So adipogenesis, as most of you know, so taking precursor differentiating to mature adipocytes, complicated, involved process, multiple pathways, PPAR gamma and CBP alpha are key transcription factors regulating that process. I'm not going to get into the details of those. But when I started kind of investigating what may be happening, one thing, and learning more about adipogenesis, one of the first things that I read about was about what are factors that regulate adipogenesis, and fatty acids, IGF-1, growth. These things are all released during or after exercise. Interesting. So again, sparking this possibility that does exercise do something to promote adipogenesis? All right. So we took to test this crudely, we took blood samples before a session of exercise in overweight adults, so that probably is irrelevant here, and took a sample right after exercise. We then took the serum from those samples and we pre-incubated human pre-adipocytes with the serum. And then we brought them to differentiation to see, is the rate of differentiation different if the samples were and we'll call the pre-exercise, the non-exercise serum versus the exercise serum. So in this cartoon, so exercise, we'll look at cell differentiation over 3 days, 9 days, and then we're comparing that to the non-exercise serum. Okay. So, and again, these factors are involved, and we use PPAR gamma, which is a classic early stage differentiation marker, and we also use FABP4 as a later stage differentiation marker. And bottom line is we found the red bars here are the exercise serum. By day 3 and by day 9, the exercise serum did induce a greater rate of early differentiation, and the FABP4 data was essentially identical. So suggesting to us that something may be released in response to exercise that may be facilitating under ideal conditions. Again, we're creating a differentiation media under ideal conditions, but there may be something there that's enhancing the capacity to make new adipocytes, right? So if you don't gain weight, if you're not overeating, maybe those signals may be there, but maybe they're not really taking hold of anything because there's not so they may not be doing anything. But if you are in a period of episodic period of overeating, maybe that is an element involved. So really quickly, we looked. So the question then is, what is it? And we don't know. That we looked very crude, poor man's version of a scan. So we looked at just the kind of the likely factors of the likely suspects. So these things increased in the serum. These didn't change. So irisin was one that didn't change. But to take this further, our plan was to look at some of these factors in isolation to see are these by themselves one of the things that may be sparking this enhanced rate of differentiation. Those are, again, these are yet to be published data, and so those are yet to be explored. So adipogenesis, talk a little bit about the role that exercise may play in the extracellular matrix remodel. So with this, I want to talk about what may be happening. One of the simple examples of what may be happening is that the extracellular matrix is a fibrotic, it creates a rigid environment. And if you are overeating and the fat is trying to be stored locally, maybe like this brick wall around the cell that's preventing that cell from expanding further, a physical barrier. There's some signaling, extracellular matrix are very interesting. We're very early scratching the surface of what else it may be doing. But this, this brick wall kind of concept may help at least give some context to what might be happening at least one level. So I want to refer to this data from Phil Shearer's lab that really help exemplify the importance of the extracellular matrix on this phenomenon. So they looked at a obese mouse and an obese mouse with collagen 6 knockout. And what you can see visibly here, and I'll show you the data here, is that the cells in the knockout, when you have less of this important fibrotic component, collagen 6, that the cells are able to expand further. They're bigger. The same, and importantly, as I note there in red, that importantly, these mice gain the same amount of weight on their intervention, gain the same amount of fat, right? So same fat, but one has the capacity to expand their cells more robustly. Bigger cells, that's shown you in the data on the right there. And looking at fasting glucose, so control obese knockout, basically returned the fact that they're much, the obese overfed animal without collagen looked like the lean animal. And then here's the oral glucose tolerance test. Again, enhanced glucose tolerance, despite the fact that they're the same amount of weight gain. So this is intriguing, and collagen 6 is in particularly, it's one of the collagens that's most tightly linked with insulin resistance. We found in studies that we've published a few years ago that again, this is people data now, that people with a higher abundance of collagen 6 also released more fatty acids. This is baseline overnight fasted rates of release. So it correlated pretty well. And so that was intriguing. And the other intriguing part is, there's the text of what I just said. The other intriguing part is that collagen 6 can be modifiable by overeating. And so these are data from the Pennington of a 8-week overfeeding study in humans. And you can see that collagen 6 in this case did increase in response to an 8-week overeating intervention. So it can be modified. What does exercise do to modify? And the exercise data, unfortunately, is limited and largely limited. In my view, at least my take of the literature is I've yet to find studies, and I'm looking at what happens with overeating and exercise. And again, if weight gain is different as a consequence of energy expenditure during exercise, then all bets are off. It's a very hard, if not impossible, question to address. So I have yet to find an overeating study with exercise that has effectively done that in humans. There's a really great series of studies by Kawanishi, who had took a mouse study looking at 4 months of exercise training in mice, and with no exercise and exercise, and importantly, the amount of weight gain was similar. So we're able to, this is apples and apples, not to me, apples and apples, right? So this is just a serious red, so kind of a global fibrotic marker, as you might expect. The lean sedentary animals didn't have much, so it would be darker stained, as you can see is the case with the obese sedentary. And the obese exercised, oh, sorry, here's the data for the serious red data. And the exercise was not completely protective, but largely protective of the gain, right? It's not reversing. So these data aren't saying that you're reversing existing fibrosis. In fact, I don't know if that can happen, but with continued gain of weight, you would likely continue to gain fibrotic content. But living a physically active lifestyle, exercising, might help reduce, if not prevent, further gain in fibrotic content. And they also measure in this study, they also measure some factors regulating the stellar matrix, so TGF beta. So it's similar kind of that the exercise really was seemingly doing this for real and mechanistic. All right. So angiogenesis. So we just recently, like last week, got accepted a publication in Journal of Physiology that we looked at 3 months of exercise training, did biopsies before, biopsies after. We looked at HIIT and MICT, we call it, as many of you are probably familiar with MICT, but more conventional, steady state exercise training, not matched for caloric. It was intended to be more of an intention to treat kind of, the HIIT was 1 minute on, 1 minute off, 10 intervals of that. So the exercise session took about 25 minutes versus a 45-minute session of the continuous exercise at moderate to vigorous intensity. So the time was much longer, the caloric expenditure was much longer. We did very tightly control, we hovered over our subjects to maintain weight. So during this 3-month period, they did not change weight. So the data I'll share with you from this study it was that capillarization did increase, right? And there are not a lot of studies. One other study that I'm familiar with that looked at training effects on adipose tissue capillarization, a lot on muscle, that's a classic adaptation to training, but that capillarization seemed in our hands to increase, right? And this increase was without any change in weight, right? So hypothetically, I would contend that with things may be different, and maybe there's even more, if there's stimulus for the tissue to be growing as a consequence of overeating, then maybe there's even more stimulus for that exercise may impart on the angiogenic process. And so how might that be happening? So just a tidbit, and I'm not going to get into, and some of you are much more sophisticated in your vascular development and so forth. But VEGF is a key regulating factor for angiogenesis. And what we did was look at a variety of different markers, but I'll focus on the VEGF. So we did a different study. Took maybe I should use a different cartoon in that to show these are different studies, but fat biopsies before and 1 hour after a session of exercise, and looked at a variety of different factors in the tissue. But the one thing that stood out was VEGF. Right? And we looked at untrained overweight adults and trained overweight adults. And in both cases, 1 hour after a session of exercise, the mRNA for VEGF was elevated. Suggesting to me, again, this is a little hand waving here, but with every session of exercise, perhaps there's a stimulus for things to move forward in terms of angiogenesis, and it may happen even in an untrained person. But again, if there's minimal stimulus for tissue growth, like not overeating, that maybe it doesn't, again, take hold, and maybe it requires kind of a prolonged overeating environment to actually be manifest in more robust capillarization than we even saw in the previous. Hopefully that makes some sense. And the last piece I'll throw in, because I'm not sure if this is a cause or consequence. It's probably both, with inflammation. And again, I'm not going to get into the details of inflammation, but I will go back. This is actually a separate study from the same group that I mentioned before, with the same cartoons of the 4-month overfeeding. Again, similar weight gain in animals that were overfed for 4 months without exercise versus exercise. And here's just F480, so kind of a global macrophage marker, and maybe not unexpected, based on the data I showed you before, that the overeating group without exercise had increased macrophage infiltration, and the exercise was largely protective. Again, this is global, not differentiating the different types, but they did present data on CD11C, so more inflammatory macrophage showed the same results. That's how the pictures would be conducive to digesting the story. But it's not just total macrophage. It seems to be that you're protecting against the pro-inflammatory macrophages as well. Okay. So we believe that, again, this is hypothetical. I want to keep saying that because we have, again, I think evidence-based to put a story together, but does it really have legs? But the story that these data tell me is that these are probably really important for healthful adaptation, so modifications in these elements, adipogenesis, extracellular matrix remodeling, and angiogenesis, and inflammation, are probably pretty important for healthful adipose tissue that maybe have a better capacity to store adipose tissue. And importantly, they don't work well in a vacuum. If you have an increased adipogenesis, for example, make a whole bunch of new cells, but you still have a very rigid, high fibrotic environment, those more fat cells can't expand any further. So maybe you're not better off, right? So you need maybe both, or maybe more importantly, the matrix. If you're able to expand the adipocyte, because your extracellular matrix is now more flexible and able to accommodate more tissue, but you don't accommodate that growth with increased angiogenesis and capillarization, then that's not helpful either, right? So, and again, I don't know the cause and effect elements of the inflammation, but certainly inflammation is important. So all of these things, I believe, integrate together to play a role. And again, I would argue that exercise is kind of the hub at being able to stimulate, or among the hubs that can stimulate these events in sync. I almost said tandem, that would be two, but in sync together. So as I wrap up, I want to make sure that I'm being clear that I'm not sure, as I note here, exercise may not remodel adipose tissue from metabolically unfavorable to metabolically favorable. The data I've shared with you today and the hypothesis is not this reversal of existing challenges, right? Its potential, perhaps best potential, is moving forward, right? And so the argument's like, well, I already have my patients are obese and they are problematic, but guess what? Hopefully they're going to live for longer, and maybe there are things that you can do to help prevent further disruption and dysfunction, right? So I'm not sure. In fact, the data that I'm aware of suggests that this may not be the case in many cases, that the reversal of metabolically unfavorable to favorable, even with weight loss, even with bariatric surgery. So what, again, just restating our working hypothesis, which is that exercise primes subcutaneous adipose tissue to be a more effective storage site for energy when we experience episodes of weight gain. And it isn't esoteric, it's because we gain weight over time, our lifetimes, right? And again, in this case, I've added maybe through increased adipogenesis, reducing fibrosis or remodeling the extracellular matrix, increasing angiogenesis and capillary growth, and reducing inflammatory insult into the tissue. So we're currently doing a somewhat of a pilot study. I'm trying to get funding for the bigger project, but to address this, we really need to do overfeeding studies. But I'll share with you, and I shared with some, kind of what we're trying to do. So we're doing a study now in a handful of subjects where we're taking adipose tissue biopsies and muscle biopsies at baseline, doing metabolic testing at baseline, so insulin sensitivity, having them all lose 10% of the body weight, randomized into an exercise-only group. I'm sorry, exercise with the 10% weight loss, or a mandated that they don't exercise, maintain their habitual physical activity behavior. And then after the 10% weight loss, do these measurements again. And to be honest, I'm not sure how much the exercise is going to play a role in that at that stage of things. I think that the weight loss is going to be phenomenal. It's going to do great things in terms of remodeling, or some remodeling, smaller cells and so forth. But the exercise may not be doing a ton. Where I think, so the other element of the study is we're going to have them then regain. In this case, thank you. We're just about done. We're going to have them regain, overfeed them to regain 5%, so bring up to half of what they lost. And that's where we think the value of the exercise will really be translated. That now, because of the exercise behavior, maybe it's not long enough, I'm not sure, but because of the exercise behavior, created this environment that can now grow a tissue that can now accommodate that energy more effectively, that we'll see the differences out at this stage here. And I think the relevance is obvious because people unfortunately experience weight regain. Exercise is actually it does a reasonable job of helping reduce weight regain, but still people will weight regain. And mechanistically at the tissue level, again, we're testing to see if this hypothesis holds. And again, what we think may be happening is that these changes, modifications to the structure may be important. So again, we think exercise may hold the key to help unlock that capacity to store adipose tissue, which may reduce this excess delivery of the energy into these tissues and reduce the metabolic dysfunction that you may experience with weight gain. So take home message, last slide. So back to the early muscle related data, exercise is known to improve metabolic health, but training induced adaptations in skeletal, and the adaptations in skeletal muscle do not appear to have profound long lasting effects on insulin sensitivity. Right? And the last are about the adipose tissue. Enhanced capacity for adipose tissue to expand healthfully during periods of overeating can protect against metabolic health complications. This healthful adipose tissue expansion requires, hypothetically, these adaptations in adipogenesis, extracellular matrix remodeling, angiogenesis together. And the role of exercise on factors regulating adipose tissue expandability may be a key component to the long-term metabolic health benefits of exercise. So with that, I thank you and thank my colleagues and my lab members who do all the work. And some appeared in, this was I think we had to take off our masks for that picture several weeks ago or months ago, but some were not available that contributed mainly to the data I shared with you. But that, and thanks to my funding sources, and I apologize for going long, but I'm happy to address any questions that you might have.
It's already 5 questions.
Yeah.
I'm curious if you started to look at any sort of sex differences, because I'm thinking about permeability of, I know sex differences is the question that always pops up.
Yeah.
Permeability coefficients within men are lower than the capillary permeability in females. So perhaps the angiogenesis that you're reviewing is actually going to be more so in male than female participants. Do you think that that's the case?
It's a great question. I think there are a lot of elements even beyond permeability issues that you're mentioning that may be a role. So in answer to your question, I do study, as mandated by NIH, I study men and women. Unfortunately, they're not powered nearly enough to make those meaningful comparisons. We always, in our studies, when they're mixed sex, which most of my studies are, we look at the sexes, but we're so underpowered that, and I think that, and this is a cheap response, but I think that I'm hoping in many cases that the adaptations are so robust that they may translate across. There's certainly going to be meaningful differences between the sexes, but I sense that there'll be enough similarities at the gross level that we're measuring that we may find that I'm okay with this similarity. But it's a really important question, and to be able to do this, you'd need 3 or 4 times or more of the population we need to tease out what are going to be more subtle than the intervention effects. But it's a really good and important point. Yeah. Oh, sorry. Vicky.
So just to piggyback on that, first I will say that I love that hypothesis. And it's something I haven't really considered before, but I love it because I've sort of had this thinking for many years that estrogen and exercise are very similar in terms of the functions that they have on adipose tissue. And one of those is insulin sensitivity. And the VEGF angle is something I hadn't thought about, but I think that's really interesting.
Yeah.
My question is about insulin sensitivity. How much do you think your adipose tissue phenotype is?
Yeah.
Maybe not. How much do you think insulin sensitivity
So
in facilitating,
interesting. So I think insulin sensitivity at the adipose tissue.
adipose?
Yeah. So I think it's, and actually we have some data now that it seems to be a really important player in those who are, I don't know about the expandability. So maybe I'm not going to answer your question effectively, and I apologize. We can talk offline about, I need to think more about it, but let me share with you that the response during a clamp of fatty acid availability during the clamp seems to be even more tightly related to insulin sensitivity. So meaning that those who are insulin resistant, and a pretty homogeneous population to begin with, but those who are more insulin resistant at their adipose tissue, every meal, they're releasing more fatty acids because they're not shutting things down, and they become more profoundly they're more insulin resistant at the muscle level. So the communication between adipose tissue and, you don't become insulin. This isn't a switch that turns on insulin resistance in all tissues at the same time. What happened, the lineage or the time course of those events is still unclear. I think there's good evidence to suggest that adipose tissue insulin resistance may occur first, and that therefore with every meal you're not reducing fatty acid availability as much as you would if you were sensitive, and that's causing, again, this what I view as being a real big problem, this fatty acid induced insulin resistance. So I hope I touched on your question a bit. Okay. Yeah, Scott.
Any beiging in your sub-Q adipose tissue?
So we do not see. So UCP1 we only measure. So we did a panel of. We did not see any meaningful measure Western blot of a variety, a small amount of adipose of adipose.
Credible as evidence that you're seeing that any of your improvement in the phenotype is driven by beiging.
No, we do. Some yes, some no, and it kind of hit and miss, and it's not significant. It's like COX-4 went up. I know that's in adipose, which is really interesting. I mean, what are the signals that are inducing that? It's not. We're not the only ones. I mean, it's fairly consistent in the literature that it's happening. I don't know how exercise. Fat isn't the tissue that's contracting. It's active because it's lipolytically active. So I don't know what's happening in the adipose tissue that may be inducing mitochondrial biogenesis. But it seems to be, again, the literature suggests, and we have some of our data supports that mitochondria at least are going up, but beiging in particular doesn't seem to be.
Do you think the signal driving your VEGF and the polarization is it hypoxia? Are you creating a local environment that's hypoxic but needs you exercise bout, or what do you?
That is the going. We're not making any measurements related to that. So we'd have to measure nuclear, like HIF1, nuclear resident HIF, so localization of HIF1. We don't have the tissue to be able to do that. But the hypothesis, one of the key hypotheses would be that acute hypoxia as a consequence of blood flow redistribution during the event may be inducing the capillarization. Yep. Yep. Yeah. No, it's a great point. So we are for simplicity using weight. Our experience has been, even with training, so the training study I showed you before and other studies we've done, with our type of training, and even with HIIT, we're not seeing meaningful increases in lean mass. So it's an important point. We are gauging our endpoints of and again, we're not time-based, it's weight-based. So it is weight-based just from a simplicity perspective. We have a DEXA, and we could have them come in, expose them to the radiation, which isn't that big, but, and then, oh, no, sorry, even though you lost the weight, it's not that, come back 2 weeks. And so we could, but that iteration I think would be challenging. And based on, believe me, I thought of that to do that. But I think based on our prior evidence that with this model of training in this population, we're not seeing really meaningful in the aerobic type of training, even HIIT, we're not seeing meaningful increases in lean mass. But it's an important thing, and we'll have the measurement, so we'll be able to normalize for fat mass. So we'll be able to take that into consideration, which is a really important point. Yeah.
There is one question in the chat.
Yeah.
Dr. Patia, first he says brilliant talk, and then he asks, is the exercise-induced adipose tissue expandability hypothesis applicable to visceral adipose?
So great question, and I think it's relevant in the terms of, I think of visceral adipose tissue as being an ectopic site of deposition. So I think that the expandability of subcutaneous fat will reduce the delivery and storage of fat in, as I could have put on in my slides, and actually in other slides I have done that before, where I had the muscle and the liver and the pancreas. I think of visceral adipose tissues being in the same camp as that, and it's only elevated, but it's elevated as a consequence of poor storage elsewhere in the depot where, again, for lack of, where it's supposed to, in this depot that seems to be designed to be the main storage site. And if you can reduce the storage, reduce the exodus or increase the storage capacity of subcutaneous fat, then visceral adipose tissue will not be as expanded. So it almost works opposite. I don't know if the signals are there to be, to really address his question, I don't know about the expandability, but I think that they're related. To me, they're related in the if we can just fix subcutaneous adipose tissue, the problems with visceral and the inflammation associated with the excessive storage in that site will be diminished, is my hypothesis. Yeah.
I get where that hypothesis comes from, but then it comes back to Mark's question, then we should really around sex differences. And we'll have more visceral fat in women,
So,
particularly premenopausal.
yeah. Well, we don't. So again, you're absolutely right. I mean, and we look at them, but we have, with N of 40, we'll have 20 and 20. And there's just no. But we don't see any. Well, so that subcutaneous is more preferred.
No, visceral is more.
So,
have more visceral fat in women.
And lipolytic rate is lower in women, and which still is consistent with the story. If and local deposition, so lower body, as you well know, people with lower body adipose tissue and pear-shaped folks have less systemic, in fact, matched, as you showed in 93, matched to lean. And so women who have less fatty acid release from adipose tissue, to me, it aligns well with their lower ectopic deposition in visceral adipose tissue. Men release more from adipose tissue, and they have more visceral adipose tissue. So I view that as, maybe I just spun it to be convenient for my own hypothesis, but I view that to be aligned. But the sex differences are super important. I don't mean to brush them under the carpet by any stretch. I just don't know how to be able to really tackle it at the level that we're trying to tackle.
Another question, when you recruit your obese individuals, at what your body fat distribution is?
Yeah. So they're all abdominally.
They're all abdominal.
Yeah.
Okay.
Yeah, that is an eligibility criteria.
Any more questions?